So, huh, so we have covered a whole bunch of topics now, and the most recent one being the idea of Turing instability in reaction diffusion systems, where you find that surprisingly diffusion under some conditions can actually destabilize homogeneous equilibria. Okay. So now let's move on. And by the way, just to remind you, I have updated the assignment, which will be due next Monday. That sort of dwells deeper into some aspects of Turing instability in the context of ecological systems. Okay, so today we will start a new topic. So far what we have done, right? We have understood spatial dynamics in the context of ecological systems, and we have done that via two sort of model. One model is that of random walk model. Okay. Random walk was probabilistic at the microscopic level. The rules, it actually had an interesting set of rules, how individuals move at the microscopic level. We call them fine scale level, or microscopic level. And then there was a macroscopic description of how the probability distribution of such a random walker evolves over time, right? So, and that gave us a diffusion equation. Okay, and then what we did was we sort of combined the birth-death process, right? Of this was stochastic, the fine scale rules, right? Fine scale, whereas it became a deterministic equation at coarse scale, right? And that was basically what we call diffusion equation. This was the spatial part, and then this was also what happens within the lifetime over very relatively short time scales of individuals. And then, of course, in the ecological context, the birth-death processes, right? We captured them via various, reaction terms, what we call reaction terms. Okay. And they were all captured by deterministic mean field, what we called mean field terms, right? So far what we have done is we have been dealing with the processes as deterministic mean field terms. For example, in the context of logistic model, we wrote something like this: Rn times 1 minus n. Okay. There were no local scale rules, right? This actually we haven't at all defined for the birth-death process. What we did was we just wrote down these mean field terms using some sort of mechanistic and phenomenological approaches. Okay, so what do I mean by these terms? I'm saying mechanistic because there were some reasons why we chose this term, n into 1 minus n by k. It was driven by the mechanism of intraspecific competition. That's why it's mechanistic. It's also phenomenological in the sense that there was no good reason to choose this form alone, right? Once we have decided that the per capita growth rate reduces with density, there are many forms, functional forms that are entirely possible. We just chose this sort of phenomenological, without really giving any sort of strong reasons, but it was more of a hand waving reason. Okay, let's keep this simple mathematical form. That was the real argument we used when we first derived logistic model. So what are but we never really bothered about what are these local scale birth-death processes, right, which are actually stochastic in nature, right? So the processes at the very local scales are indeed stochastic, but we have never defined that. So what we will start doing now is to define this, in some sense equivalent of the random walk, random walk rules, where we had stochastic rules of how animals move at very fine scales. So what are those? And then how do we make link between these two? Okay, so this we were able to do very well, right? So starting with the stochastic movement tool, we derived the deterministic coarse scale diffusion, or it could be drift diffusion, depending on whether it was biased random walk or unbiased random walk. So we got one of these two equations, right? So how do we, what's the equivalent here? So we need, today the focus will be sort of start writing these kind of rules for birth-date processes, and then ask the question, how do we then scale it up? Okay. So let's do that with an example. Okay. So an example of stochastic birth-death process. Okay, so there are many ways of doing this. There is no one way of doing it. Okay, so I'm going to present one such example. Okay, so I'm going to describe a model called contact process. Okay, but my contact process is a very well defined process in applied mathematics. It's a it's a Markov chain with a very beautiful set of properties, and a lot of work has been done in the context of stochastic processes. So I'm going to introduce some set of rules for birth and death inspired by this. So mathematically, if you work it out, the properties of the contact process and what I'm going to show today will be qualitatively similar. Some features, some numbers might be different, broadly they are. Let's do this. So what do we do is do this is basically a spatial stochastic model. Okay, it was originally conceived in the context of spread of diseases, but it can be applied in many other contexts. Okay, so what we do here is again consider a space which is divided into a large number of grids. Okay, now unlike the case of reaction diffusion grid, okay, here there are some fundamental differences. Okay, here each grid or each grid cell, okay, can have only two discrete states. We call them 0 and the other one being 1. Okay, 0 is basically unoccupied, 1 is occupied. Okay, you can think of 0 is clear, it's unoccupied or a bare state. 1 is basically occupied. Now we can think of it as occupied by, for example, a tree or an organism. But as the rules will show you, you should think of this as organisms by that actually move slow. Okay. Okay. So each of these grids could be bare or or occupied. Okay. And that's the first important aspect of this model. Okay, it's discrete space. Okay, that's very clear because it's a grid cell, and then there are discrete states. Okay, so space is discrete. Okay, now let us just recall what did we do in the context of diffusion when we were deriving diffusion equation. The space was discrete entirely for the purpose of only for the just 1 second. Sorry about that. Okay, so recall that we were thinking of again grids of similar type, but there are two fundamental differences. The space was discrete only for only for the purpose of convenience, okay, but the space was actually continuous, right? Okay, we eventually took the grid sizes to be going to 0. Okay, that's space was continuous. There's another important difference, which is that states. What were the states that were possible in each of the grids in diffusion? It was a continuous state. It's a it was a probability density. It's a concentration of organisms. So whereas here it's literally one organism or 0 organism. Okay, so that's important difference between when we were using a similar grid, spatial grid for studying population dynamics or the diffusion. Okay, so but here in the stochastic birth death model, the space is discrete and each cell has discrete states. Okay, so now that there are these zeros and ones, we define a bunch of update rules. Okay, and these update rules take over discrete time steps, but except that in this case, this is not a very crucial assumption. Okay, so discrete, for I'm going to put that in quotes. The way we are going to define will be still discrete time steps, but for reasons that I will probably explain a bit later, it actually effectively can be thought of as continuous time steps as well. So what are these update rules? Okay, basically when I say update rules, think of bare areas and the cell with tree, right? There are going to be birth events, there are going to be death events. So these update rules correspond to that. Okay, so the way these update rules are defined is as follows. Choose a random cell. Okay, if it is unoccupied, if you hit 0, choose another random cell. Okay, if you hit 1 in your random selection, okay, two possibilities can happen. Okay, first is that of birth. Then how does the birth happen? Okay, the birth happens with probability P. What you basically do is you now pick another random neighbor. Pick a random neighbor with probability P and germinate. If that is empty. Is it fine? So if we write that in the following way, 1 was the first chosen cell, right? And if the neighbor was 0, this becomes 1, 1 with probability P. Okay, so 1, 0 can become 1, 1 with probability P. So this is the birth process if 1 has been chosen. So birth happens with probability P. Of course, it can also lead to death. But this happens with probability. 1 minus p. Okay. What it means is you chose 1, it becomes 0, probability 1 minus p. And then keep repeating this process. Keep repeating these rules. These rules. Are the rules clear to everyone?
Why does the death probability necessarily have to be 1 minus p? Can't it just be like anything and nothing happens in that particular step? Like it doesn't jump, it doesn't die also.
So you're saying, do you want another probability d instead of 1 minus p? Is that what you're saying?
Yeah, instead of saying
an independent
the inverse
parameter.
The reverse of birth is death. Instead of saying that, it might
you can do absolutely do. Yeah, there's no problem at all. I can if you want, I can do it right away. It makes no difference to the rest of our calculations. In fact, I know I just encourage that you try it yourself. Is it fine?
Sir, what if the cell is 1, 1? Like if the random neighbor has
so basically then nothing happens in that case. If you pick 1 followed by another 1, nothing happens. You pick another random cell because you can't germinate anywhere. So yeah.
So this is an infinite grid then, like there will always exist empty cell.
No, it doesn't have to be infinite. Why does it have to be infinite grid?
So what if the grid is like full, then there won't be any birth. The probability p is not a constant then.
But this can happen, right?
Or the death can, okay.
Right? That will create empty spaces.
Okay, fine.
With p and 1 minus p, right? If you start with all ones, right? Then as long as p is not 0, as long as p is not 1, it means the death probability has a finite value. Then some empty cells will be created. Yeah, go ahead.
Is there any restriction to like how far the neighbor can be? Can it be? It has to be like immediate neighbor, or like it can be like anyone?
Yeah, so that's a good question. Usually for our purposes, we define what's called, I think, this is the focal cell. Let us say, okay.
Yeah.
We pick 4 nearest neighbors like this. Is it clear? So this is called von Neumann neighborhood.
Okay.
So what I have done is I have actually not defined formally the way contact process is defined. I have defined an implementation of contact process. Okay, I think there's a small difference between the two. Mathematicians define the process slightly differently. So you should just look that up also. So basically, the way if there are some update rules, right? The way I have defined is actually fairly clean. It actually tells you if you have to now simulate it, how exactly to do. Okay, but basically, in fact, if people see just these 2 rules, 1, 0 and 1 going to 0, usually they sort of the rest of the stuff are usually not too important. How exactly you implement can vary a little bit, as long as you define your neighborhood clearly and so on. Any questions on the model?
How exactly is the discrete time model? Is it like
why is it discrete time?
No, like is it like all the cells has to choose one of these conditionals, or is it like each cell undergoing like if we may not choose some cells, something like that?
See, basically, thing is, just think of, okay, let's say in your work, let's say you have n by n grid. Okay, let's say there are, let's just put some random 1s and 0s. I don't think I'm doing it randomly enough, but I'll try my best. Okay, I think I have a strong clustering tendency. I just noticed. Okay, so let's see, these are all the elements, right? Now, maybe this could be the first cell I picked. Okay, which means if 0 is picked, nothing happens, right? So I have to pick one more now. So the second one might be this. Again, I have to pick one more now. Third one could be this. Then I have to pick, I have to now choose with probability P either a birth or a death. Okay. With probability P, what I will do, I will pick a neighbor. That neighbor could be one of these 4 neighbors. Okay, let me now, given that this is my focal cell now. So this will be the 4 neighbors now. If I have chosen the birth with probability P, I pick one of the neighbors. If that neighbor happened to be this, then this becomes 1. But if the neighbor was one of these 3, then nothing happens. Okay, these things happen with the probability P. On the other hand, I could have chosen death with probability 1 minus P, and that happens if that is picked, then this will turn with this focal cell will become 0. Okay, so that's the way the rules will be implemented. Now, as you can clearly see, there are 2 things that can happen. Okay, let's say there are now n by n cells, right? If you now iterate n square times, if you update this n square times, on an average, we can expect that all the cells have been visited. Okay, that's only on an average, right? But what's more likely, there will be some cells which will be picked actually more than once. There will also be some cells which will actually not picked at all in one full set of iterations. When I say one full set, I mean n square iterations. Okay, so you can, in this model, you can say that 1 time unit, okay, is n square updates. That forms your 1 time unit. Okay, did I answer your question?
Yeah.
But there is no really that there is a thing that distinguishes the end of, let's say, the update rule that happens just before completion of n square and the one that happens just after n square. So in that sense, it is a there is nothing discrete about it. Okay, so what it is the following. More importantly, these constitute what we call asynchronous update rules. So time being discrete is really more of an artifact of implementation. It's not a real mathematical, property of the model. But what is true is an asynchronous update. Okay, the meaning that each event is happening independent of each event is not happening. Each event is happening on its own, and it's not synchronized with the birth and death of everybody else in the landscape. But now think of what was happening in the context of when we were simulating, let us say, when you are numerically integrating an ordinary differential equation, right? So when you numerically integrate that, there it appears as there in that step, what happens at t plus delta t depends only on what was at t at a previous time step t, right? And every cell, if you were doing a simulation of reaction diffusion equation, every cell was updated synchronously. Okay, but here every cell is not updated synchronously. Okay.
But in a way, we could also argue that in the numerical simulations also we did a for loop which was here.
But that for loop is our implementation. It's not the property of the differential equation.
Okay.
So in fact, the code sent by Chinmaya, I think, right? If I don't know, I hope I got the name right. Chinmaya, what he was doing was he was actually parallelizing that for loop process, which means, in fact, exactly the whole idea of parallelizing is, because the new state of a cell in the reaction diffusion system, right, depends on what was at a previous discrete time step. I could just disentangle the updates on every cell, but that cannot be done in this in this stochastic update rules anymore. So parallelization will fail in this case. Okay.
Sir, so
Okay.
just one more question, sir.
Yeah.
The actual birth depth depends on the dimension of the grid we're considering, right? So for example, like the number of possible grid squares around it.
And the number of neighbors, so on and so forth. Yeah.
So like if we take like, for example, this 2D grid, we have 4 possible neighbors, direct neighbors. We can also extend to 8, I guess. But like what happens if we have like, just to clarify, when we have like multiple spots open, each one independently has a probability P of germinating from the this thing. So if like say the one is surrounded by zeros entirely, each spot has an independent probability P of giving rise to a 1.
Say that again. So your question is, if there is one focal occupied cell, and if everybody else is, let's say, 0 in the neighborhood.
Yeah. So basically, if you have multiple.
So what's the question that you're asking?
So if you have multiple spots, does each one have an independent probability P of germinating in the time?
What do you think?
I would say yes, because like seed dispersal and all happens, and
no, think based on the rules that we have defined here, no. So the way to think about this, choose your focal cell to be a 0. Okay. And then look at how many of the neighbors are occupied. Right. And then, and then you have to do it calculation very, very carefully. You have chosen a focal cell 0, and then look at how many of your neighbors are occupied, and each of them can potentially germinate this focal cell you have chosen now, right? So what the probability of the focal cell getting germinated is that is equal to probability of how many of them are occupied in the neighborhood times the probability that when the update for that cell happens, that germinated cell happens, you are chosen as the neighbor. Okay, so you have to account for both of these.
Yeah. So are we taking like an equal probability that each particular neighbor could be chosen?
Hi, that's right. All the neighbors are chosen equally, because I'm not favoring a neighbor in this step. Right? I'm not favoring a neighbor in this step. It could be any of the 4 neighbors. Pick a random neighbor with probability P. Okay. So when I say this statement must be read carefully, what this basically means, maybe a better way of writing this is the following. Okay. Birth happens with a probability P. Oh, yeah. That's not actually true. That's not actually true. Pick a random neighbor with probability P and germinate if it is empty. Okay. Now, if you don't pick a random neighbor, then you do this step. I think what I have written is fine. Okay. Because probability P doesn't guarantee germination because the neighbor you pick might already be occupied. Okay.
Wait, so if some of them are partially occupied, does it
What's
get
a partial occupation?
Like I mean, like if you have like 4 grid squares around like possible neighbors for a site that's creating germinations, and say one of them is occupied.
Yeah.
Then doesn't the probability of I don't know, a germination in the other 3 things increase as well? Like, or are we picking like a P and then saying that? Sorry, I'm kind of confused.
No, I understand what your possible confusion is. I think let us not conflate 2 different issues. Given that there is a occupied cell here, what is the rule that you are going to implement? That is what this is describing. Okay, how will you implement the birth rule? That is what this is doing. Okay, which is not same as the inverse problem. Okay, if I have a 0 as the focal cell, I think what you are asking is the following question, right? And some of them are occupied, some of them are not, right? What is the chance that this will now get germinated? They are 2 different questions. You can answer this question starting with these rules. I haven't gone there at all. Okay, I am just telling you how the birth process works. Is that clear to you?
No, my question is slightly different. So what I'm essentially asking is, what exactly is the probability P of, like, what exactly is it? Is it the probability that an empty cell ends up germinating, or is it the probability that a particular cell is chosen?
P is the probability. No. It's not. You're not choosing a particular cell. No, you're choosing one of the neighbors with probability P. Okay, and then so the P is the probability of choosing a neighbor. Yeah, that's what it is. It's not a probability of germination. Okay?
So are we like, yeah, so like how, like each one has probability P, will that get split like accordingly in the, like across the three, across
again, so when you're saying split, you're now changing your focal cell. No, you have gone to what is the probability of these guys now, right? Being picked, which is not same. Probability of any of them being picked is 1/4, right?
Right. Okay.
In this case,
Yes.
given that there is a focal cell here, then that's actually 1/4. And because the birth will be implemented with probability p, it will be p/4. That's a different question. And then so that it does get split into four parts for each of the cell. Yes. Does it answer your question? But there's a very good reason why I'm not answering that question very clearly, because I'm defining the process, with respect to focal cell who is occupied. Okay, I'm not defining a process with respect to a cell who is empty and surrounded by neighbors. There is a subtle difference between them, and a very important one. Okay, is it fine?
Yeah.
Okay. I think this is a new way of doing things. It will take some time for I think everyone to sort of slightly get used to this.
Sir, am I audible?
Yeah, you are.
You had mentioned that we are doing this updates asynchronously. So like we're not doing all of it simultaneously, right?
Absolutely not. Yes.
So then like wouldn't the end result depend upon like the exact order of the blocks that we updated?
Yeah, the order of blocks was chosen randomly, right? Your answer is right. It does depend, but the order was chosen randomly.
Okay, so then like aren't we kind of like restricting the model a little bit? So like we're randomly choosing the how are we implementing that? Like
so we choose, as I said, choose a random cell.
Right. Okay. Yeah, I think I get it now.
If it is 0, again choose another random. If it is 1, do either birth or death, birth in the neighborhood or death of the focal cell, and then go back to this, choose a random cell.
Okay, I see.
Keep on iterating this.
Right. Yeah. Thanks.
So what basically your question is, if there was some configuration, if you ran n square updates, the outcome of those n square updates, let's say, is some some outcome. Okay, let's call that O1, a new grid called O1. Okay, let's say now you go back to the one previous, and just go back to the same the original given configuration of the matrix, and then you repeat the n squares updates again, but following the random protocol. So you'll end up with another outcome O2, and O1 and O2 will not be same, because every step has randomness in it, and that's the whole point. We want to capture those randomness. Therefore, one must not compare O1 and O2 directly. What you must compare are mean properties. Okay.
Yeah, that makes sense.
Yeah.
Also, we are not making any clear-cut distinction of generations, right?
Absolutely no, you're right. Yeah. Okay. In asynchronous births, we don't make that. Okay.
Sir, so among n square updates, from the second update till the last update, do we consider the grid at the beginning of the time cell or the grid that results from the previous update?
The grid that results from the previous update.
Okay, sir. Thanks.
So if you are only considering the one at t is equal to 0, then we would be doing synchronous update.
Yes, sir.
Okay. Yeah. All very, very good questions. This is very good to clarify all this. Okay. Let's move forward. So how do we make sense of this now? Okay, we have written all these rules. Of course, you can, all of you who know coding really well can actually implement this, because I have defined all the rules clearly. And in fact, as you're, actually it's not very obvious when you read a paper, when they define these kind of probabilistic rules, you will often find that, all the steps are not properly defined. And when that happens, there will be multiple ways of implementing some of the details. And that can, that usually should not change results by a great margin if the, if it's a well-defined model and, if it has general properties. Okay. But, one must be careful to make sure, the exact rules of implementations are, well understood. Okay. Now that we have these stochastic update rules, can we make some analysis of this before going to numerical simulations? Okay. Okay, and indeed there are methods that help us do this. Okay, and one such method is called mean field approximation. Okay, so we have used this term before, mean field model. Okay, now I think you will probably understand this in a new light. Okay, something called a mean field approximation. Okay, so what do we mean by mean field approximation? I hope you will understand by the end of this. Okay, now the basic idea is that we had this grid, okay, where the local states are all defined. Okay, now and as you can see, there are lots of spatial variation. Okay, so the idea of mean field approximation means to sort of ignore spatial variations. You would think, oh my God, the whole point of writing this model was that I want to understand, space and stochasticity, but this is actually ignoring spatial variation. And the mean field approximation that I'm going to do today will also ignore, I'm going to call the deterministic mean field approximation. Which by sort of, the term itself, as the term itself indicates, will ignore both space and will ignore stochasticity. Okay, but there is a very neat way of doing it, and it often provides a very useful starting point for a lot of these kind of stochastic spatial models. The basic idea is as follows. Let me present this in a very general way. Okay, there are two states. Consider any two-state system. Let's say there are states are A and B. Okay, let's say P of A indicates probability of finding state A. And likewise P of B. Now in any stochastic process, we define transitions between A and B. There are two states, and therefore there is some way A becomes B and there is some way B becomes A. Okay, so we usually denote them by T. And T, B becomes A. So these are the transition rates. Given that there is a state A, what are the rates by which they convert between the two? Okay, so given all these things, we can write down the following equation. What is the rate of change of the probability of finding the state in A? Okay, dPA by dt. What would this be? Let me know if you agree with me. This is, now, so this is the probability is changing over time. Now remember what we did when we were writing a similar equation for diffusion equation for the random walk. We started off with random walk of individuals on a landscape, right? We wanted to know where are the animals, where is the animal located and how it is changing over time. So the approach we took was, let us focus on some location X. We will look at the chances of it hopping into that location and hopping out of the location. So there's an inflow and an outflow for that location. So we think exactly that way here, the inflow rate and the outflow rate for the state A. So the inflow rate depends, let me know if you agree with this, is basically inflow usually happens, now in this case happens from what? Inflow happens from D. Okay, which means that probability that you have a state B and then that state transitions from B to A. That's the inflow to state A, and we have the exact opposite for the outflow. Is everyone happy with this? A very intuitive expression. This is called master equation. Okay. The master equation for PA. Okay. Master equation basically tells the flow of the probability densities. Is everyone fine with this?
So are we assuming that A and B are the only states?
Yeah, we are considering a two-state system, and it shouldn't be too hard to generalize it to n number of states. And in fact, the random walk was what was the dimension of the state space there for random walk?
2, right?
It was actually infinitely large, no? The space is continuous. Even if it was a discrete space, even if it was like an integer lattice, you have to go all the way to minus infinity to plus infinity, right? Okay. So it was actually, so you can define this for any number of states. So except that now you will have, if there is a, you should be able to think through this, let's say the current state is A, right? If B has many forms, let's call them B1, B2, B3, whatever, up to B infinity. The first term becomes a summation over all the B's, right? And the transition probability of all the B's to A and the opposite of it. So yeah, this is very easily generalizable with summations. And if that state space is continuous, then you have integrals instead of summations. Okay. So now let us apply this master equation in our context, which is the stochastic spatial model. So what's A for us? A would be 1 occupied, and what's B? B would be 0. Okay. Now what does P of A mean? Okay, now shall we now write down this? Now that we have identified, shall we write down the next thing we should now do is transition rates. What's the transition rate for 0 to 1? Shall we go back to the roots and check? How does 0 become 1? This was precisely the question that one of you were asking last time. How does 0 become 1? 0 becomes 1. When does it become 1? If if there is a neighborhood, right? Okay, that is occupied, right? And then it chooses this specific neighbor for updating. Okay, so under these two conditions, it becomes it becomes updated. Now here is the approximation. Some approximations come in. Okay, so what do you need? You need that the neighbor is occupied. What's the probability that the neighbor is occupied? That is P of A, right? Okay, so now basically imagine you are looking at a state 0. What is the probability that any of them are occupied? That is the definition of P of A, right? P of A is probability of finding a state A. Okay. And what should happen? And the birth also has this. This entire rule get executed only with probability P, right? Okay, so it's not just that is insufficient. It must also execute the birth rule. Okay, so the transition probability from 0 to 1 is PA times P. You should think for yourself what happens to those 4. Okay, so please think about it. What you should try to do is just work out precisely what if we had a 2-dimensional world. 1-dimensional world should be like this versus 2-dimensional world. Okay, will this always be the oh, I should actually not write 0 anymore. I should write this as P of 1. Okay, so I will leave that as an exercise. This will be P1 times P. Does dimensionality matter? Think of 1D, 2D, and 3D. Okay, I won't answer that question. I will just write this as P of 1 times P. Okay. Now, what about t of 1 going to 0? Again, go back to the previous slide. What is this? This is basically -1 minus p, right? Does it depend on p of whatever? No, right? No, mean the pro. I'm sorry that I'm using p for to mean to sort of p as the small p is basically that the birth death probability of the microscopic rule. I should be writing it better. Capital P is the probability of the state itself. Okay. So this is a different p. Let me try the curly p. Is it clear to everyone? Is everyone happy with this? So if you now apply this, let us write down the master equation now. So dp curly p, okay, dp1 by dt is equal to probability of p is what? Probability of 0, right? Times this was probability of 1 times small p minus probability of A is probability of 1 again times 1 minus p. Is everyone with me? Okay, so now, so what is p of 1? P of 1 is basically probability of finding the state 1, right? It's the occupied state. So we can interpret probability of finding 1 at any state as the density of organisms. Is that fine with everyone? Let's denote that as rho. Okay, and conversely, P of 0 becomes density of the occupied state or the base state. That just becomes 1 minus rho. Okay, so with that, what we have is left hand side becomes dou d rho by dou t. So rate of change of density of organisms is given by, okay, this is rho, this is 1 minus rho, this is p. So p into rho into 1 minus rho minus this is just rho times 1 minus p. Okay. So again, let me just remind a small exercise. Does this equation depend on dimensionality? Does this equation spatial dimensions? What's your guess? What's your hunch?
I would say no.
Why would you say no?
Because the rho is just like, I don't know, it's a count as opposed to like, it's a fraction of the.
It's a proportion. It's a proportion. Yeah.
It's a proportion, and the probability p is just like independent of space. Oh wait, that might.
Okay, just work it out. See what you find. Okay. Now it's a bit tricky. Depends on how we count, how we count the probabilities. Okay. Yeah. So this is the mean. So this is called the deterministic mean field approximation. For the model that we described, okay, for our spatial stochastic model. Okay. Any questions before I go forward? So let's analyze this now. So what we have is basically a standard dynamical equation, right? Now, which we are now experts in solving this, right? So what we do is basically take all the row terms and take all the row square terms. What do we find? We have row square, row dot is equal to, so let's look at p row is the row term here, and then you have my p minus p row square. So we have one row term here, p row, and then another p row, right? It's 2 times p times row. Is it correct? And then you have again another row term here, which is minus row. So what I think will happen is we have 2p minus 1, if you put them all together, times row. That will be the linear term. Is that fine? So 1 minus p is already a linear term, and then you think of just adding this p row term. And if you now account for the minus sign, this becomes 2p minus 1 times row. That's the linear term. Okay. Now, what are the nonlinear terms here? There's only p row into this one. It comes with a minus sign. Minus row square. I hope I have not made any mistakes algebraically. Okay. Okay. So now we can find the equilibrium. So what are the equilibrium solutions? Equilibrium solutions are when this entire right hand side is equal to 0. That happens when either row is 0 or, so if I take the row common here, so 2p minus 1 minus p, that's another solution. There are two solutions. One is an extinction equilibrium. The other one is a non-extinction equilibrium that follows 2p minus 1 divided by p. Okay. Now let us look at stability. What do? We take the right hand side and take the first derivative. So it becomes 2p minus 1 minus 2p rho star. That's the f prime rho star. So let's calculate this at 0. So f prime will be 2p minus 1. So therefore, rho star is equal to 0 is stable if this is less than 0, right? So extinction equilibrium is stable if, when is this negative? 2p minus 1 is less than 0, meaning p is less than half. Okay. So we can now guess without thinking, right? We now know enough about ordinary differential equations and the stability and so on and so forth. If there are two equilibrium, when one of them loses stability, what happens to the other? The other now becomes stable, right? So I can do it without doing any work, that 2p minus 1 by p is stable if p is equal to half. And also note that when p is actually equal to half, the numerator here is 0, right? So these two will just coincide. So these two roots have become identical. These two branches become identical. Then p is equal to half. So we can now try to plot this as a bifurcation diagram. So rho star, this is p. Okay. So you have, what's the maximum value of p, by the way? Being a probability, it is 1, and then you have half. Okay. So between 0 and half, what happens? What's the stable state? So stable state will be 0. Extinction is the stable equilibrium. And after that, it becomes unstable equilibrium. Okay. And then between 0 and 1, let's again see what's the maximum value of p. P is 1. What happens when you set p is equal to 1 for this? It becomes 2 times 1 minus 1, that is 1 divided by 1, 1. So when p is equal to 1, this also reaches 1. Okay, and it doesn't go beyond that. And at p is equal to half, it is 0. So do you think, so how does it reach? Again, if you just work it out, you will find that it's obviously not linear because there's a 1 over p term. It reaches 1 like sort of in asymptotic. It's a very, I'm really sorry, it's a really bad writing. I'm writing for this time. Sort of like this. Okay. So this is the one asymptote for 1. Okay. It reaches 1 at 1. That's not bad. Okay. Okay. Do you all agree with this? So this is called a mean field phase diagram. The word phase diagram comes from physics. So people used to do mean field approximations for determining the phases of materials like superconductivity, superfluidity, magnetism, and so on. Okay, it's called the mean field phase diagram. It makes a prediction that PC, critical value of birth rate, is half. If it is less than that, what you see is extinction, where everybody is 0. Okay, this is an extinction phase, right? Whereas this is an active phase, meaning there are live individuals, right? Active phase and extinction phase. Okay. And this extinction phase also has an interesting feature. If everybody is 0, can a spontaneous birth happen in the set of rules we have described? If everyone is 0, what happens to these rules? Independent, let's think of any value of p. Okay. If everyone is 0, what happens? You do this, execute this. If 0, choose another random cell. Can you ever find 1 if everyone is 0? No, right? So you basically end up executing this infinitely large number of times. And in every one of them, nothing is changing, right? So therefore, 0, a grid full of 0 always remains 0, independent of the value of p. Okay. So that's why this state, rho is equal to 0, is also called an absorbing state. Okay, if you are there, you can never come back. Can never have any active sites anymore. Even if the active state is stable, because everybody is, now that of course makes sense in the context of extinctions. When you have extinction, you can't have spontaneous birth of individuals, right? Okay, and that makes perfect sense.
Shouldn't the rho star is equal to 0 state be stable for all values of p, sir?
Why so? We just proved, right? It's not.
But then going back to the spatial model, if none of the grids are occupied, they can't reproduce, right?
But if you now introduce a perturbation, so how it remains stability? So perturbation, say I added 1, maybe a small number, very small but infinitely small number of 1s, right? The question is, can they now take you away from the 0 equilibrium? Rho star is equal to 0 equilibrium. Oh, that's possible if p is greater than half is the prediction of the mean field theory. Okay. This is also called, for example, physicists will also call this mean field theory, by the way. This equation will be called mean field theory. Okay. Fancy name, so useful to know. Okay.
Aren't all the fixed points observing states then?
Which are there's only one fixed point, no, two fixed points. No? This one. Why is it absorbing? Let's say if everybody is one, okay, other extreme, okay. If everyone is one, can some of them become zero?
Yes.
That can happen, no, because of the death rule.
Yeah.
Right. So death doesn't require the presence of dead individuals around. Whereas the birth does require the presence of living individuals. Okay. Any more questions? So now I would now certainly encourage that you think of incorporating this using numerical simulations. Certainly. Okay. So let me just do one more thing for today and leave another small exercise for yourself. Okay. So let's now improve this model a bit in addition, extension to the model. Okay. So one extension one can do is the following. You know that in many ecological contexts, we have competition. That's one very important interaction, right? Okay. So it's worth thinking, how is the competition included? Does contact process the version that I presented, does it have competition in it? Huh?
No.
There's no competition. If so, why don't you incorporate it? Okay. So think of how to incorporate. Okay, one way to think about this, crowding causes additional mortality, right?
So add a critical neighborhood population.
You should think about how to add. There are many ways of doing it. You just think how to do it. Okay, that's one way.
I had a question. Isn't there like competition for space in some sense? Because if there are too many occupied cells, even if even if you for a given cell, even if you are germinating, you have no place to put it, right?
Yeah, it's an extremely good point. So now think of a world without competition, right? What would have happened? Let's say you are somewhere here now. If there was no competition, why did it stabilize at a value less than the maximum value? Maximum value would have been 1, right? Meaning every cell is occupied. Okay. If you thought there was no competition, right? Why did it actually stabilize here but not go above, right? Okay. So if you think about that way, as Rutuj is rightly pointing out, there must be some competition. In the absence of competition, things would just blow up, right? Okay. So, and in fact, where is that coming from? And as Rutuj pointed out, it's exactly by the fact that there is competition for space. Okay. Okay, but you should think and convince yourself that it is indeed the case. Okay, so competition need not be for resources alone. Competition can also happen for space, and in fact, space is a resource. Okay, so you're absolutely right. In fact, there is competition here, and it's for space. But this competition could be thought of as crowding leading to lesser food and therefore additional mortality. Okay, so think of incorporating this and then find out how this phase diagram will change. Okay, so another thing to think about is another ecological interaction which is very important is the inverse of competition, which is facilitation. What does facilitation do? What does facilitation do? As the name indicates, it's a positive interaction. So for example, it basically means that there is an increased chance of birth. Another way facilitation can act is there's a reduced chance of death. Okay, increased chance of birth and a reduced chance of death. Again, think how will you incorporate this? Of course, there are going to be many ways of doing this, and then you can think of other types of interactions. What if there are cooperative interactions? What happens in cooperative interactions? I think a lot of people may not know the difference between cooperation and facilitation. So usually in cooperation, what happens is, there are two types of individuals. Let's call them type A and type A. Okay. If they are together, they cooperate. But there are also another type, AD. When they happen, what this happens is, in this case, these guys will cheat. Okay, and this leads to some interesting sort of interactions. Okay, so read about them and again think how will you incorporate that in a spatial model like this. Okay, so I'm not going to give you answers for any of this. I would like you to think of these scenarios. Okay, so we'll actually stop here. We'll get back on Friday and we'll do some exercises on extensions and writing your own mean field models. Okay, but you should start thinking about these new type of models. But I understand that you also have a homework due, so you will not, some of you may not be able to spend too much time on this, but we will take it forward on Friday. Is that okay? But it's a basic idea of how to write a mean field model, create everyone. So sort of, the key is to understand that there is this master equation, and then you should just know how to write these transition properties. Once you can do, you can know how to write the mean field model. Okay.
Sure. Conway's game takes care of 1 and 2, right?
What is 1 and 2?
Yes, sir. Computation and facilitation. Yes, sir.
I don't remember the exact rules, but probably does. Not very sure. It's been a really long time since I read that. It's a very sort of toy model of some sort, right?
But Conway's game was deterministic, right? It's purely deterministic.
It produces this very sort of crazy patterns all around. Yeah, that's right. That's a very good point. Yeah. Okay, cool. If there are no questions, I will stop here. We'll resume on Friday.